Right, so I'm going to talk about this mouthful of a title, which includes what I did for my thesis project and a little bit more. So let me start describing what is the main result. So I'm going to start with some setup. So f over some CM extension of number queues. And soon I'll take f plus to be q for ease of notation. But for now, let me stick to the full generality. V1 and V2 are two rank R non-degenerate Hermitian spaces. And P is going to be there. So attached to this, I consider a pair of reductive groups. The groups of F plus. And these form a spherical pair. So I'm going to be interested in H period. This is what's often called unitary Friedberg Jacquet period. And it's the period function. Of H. Like F maybe some. That's the automorphic part. Right, so as I said, this H inside G is a spherical pair. So these periods are very interesting. And there's a conjecture for exactly what they see, which fits in framework of relative lengths. So this was first stated by Liang-Xiao and Wei-Zhang. So if pi is some tempered that's the automorphic representation of G, this period restricted to pi is non-zero if and only if. So the part that's going to play a key role in the stock is that it's the central L value of the standard L function for the base change of pi. But this should be non-zero. But also to make this actually an if and only if, I should add that this base change is symplectic. And that pi is locally distinguished. So we have good deal of partial progress on this question. So pull up one Sidbar in 2019, and also Cheng Gang.
Right, but bigger, please.
Sorry?
Bigger.
Bigger, yeah. 2022. So they prove many cases of the Fourier implication that I wrote. If the theory doesn't vanish, then these conditions are satisfied. And there's upcoming work of Leslie Xiao and Zhang with a relative fixed formula approach. Which will settle this conjecture in some cases. Right. And so mostly for the purpose of this talk, I'll kind of think of this conjecture as given, because what I'm more interested in is these Bloch conjectures. So in cases that this automorphic representation has an associated Galois representation, so where the basis was often called relevant. So it's serially reducible, conjugate self-dual, and at the Archimedean places, it's irreducible principal series. This.
When they prove that in their partial cases, do they get it in the form that L is the period squared?
They get like the confusion indicated. I don't think so. And even the relative trace form approach will not establish just the non-zero implies non-zero. Yeah, so in cases that this is relevant, we have by work of Genevieve Harris. Uh, 13. We have some associated Galois representations. So at each Archimedean place, it's the irreducible principal series, but it's carried. So R is the argument. And conjugate self-dual and irreducible. I'm just not going to write everything. Right, so we have attached Galois representations. So here, E is some number of fields that I won't care too much about. So I'll also take it to be Q just for ease of notation. And then the Bloch conjecture. Conjectures that first. That is L value is non-zero. Now we have a certain Bloch the Selmer group functions. So this Bloch conjecture is in sense some vast generalization of Bertolini and Darmon. This is some kind of rank zero case. Right, and basically what my main theorem is the composition of these two forward implications. So in some cases, so I'm going to assume that both these Hermitian spaces are totally positive definite. And as far as I understand, this is also a condition in this relative trace form approach. So I'm also going to assume that the space change is relevant. So I can phrase this as this pi infinity is trivial, right? This being totally positive definite means that this the Archimedean points of these groups are compact. So I'm saying that this representation of infinity is trivial, and the base change is irreducible. Right, so this. Means that the space change is relevant. And also for some technical conditions to do with cohomology mervates, I need to assume that F plus is not Q. Right. And if lambda is admissible, and I'll say a little bit about what this entails. Now we have what I said before, the composition of the two forward implications. So yeah, I think of this as some evidence for this rank zero case of Bloch. Is that I kind of think of that conjecture as Kato. Right. So of course I didn't tell you what admissible is. So let me say a little bit about this. So this admissibility is a long list of technical conditions. Let me try to give some flavor of some of the things I need to assume. So as I'll talk in a bit, this uses this machinery of Euler systems. And whenever you're doing some Euler system argument, you need to assume some kind of big image or something, some kind of big image for this Galois representation. There is also some technical conditions that are Galois deformation. Periodic conditions. To ensure some adequacy here. And there's also some conditions to ensure that we know some homologs of Cauchy-Word varieties. So there's some homologically homologically generic assumptions and some other more mild assumptions. But it's worth pointing out that we expect these to hold for all but finitely many primes, as long as this representation is kind of primitive. It's not a transfer from smaller groups. And maybe if you want a concrete example that you can actually verify these, if this Galois representation is the 2r minus 1 symmetric power of the Galois representation for some modular root curve. And non-CM. Then indeed, all but finitely many primes are admissible. Hopefully this gives some sense about what this admissibility condition looks like.
So anything about what homologically generic means?
So this is ensuring that your representation only shows up in the middle degree of homology.
Gotcha.
Yeah. And I think this is already, this we know it's all but finitely many. Maybe Fat plus is not Q. So really the hard ones are these two.
Yeah.
Yeah.
Sorry, can you say more about this Galois deformation theoretic condition?
So that is a part that I at least know about. So maybe no, for now, we can chat a little bit later, a bit more about it.
And also,
I don't, yeah, this is relying on works of previous people. In particular, this article, see, I don't need to do any Galois deformation, deformation periodic arguments.
big image is big image is the image of row, not row part, not the residual.
Right, well, it is a priori of rho, but in fact, if the image of rho bar is big enough, that will suffice. So you can think of the residual representation. yeah, this implies it's absolutely irreducible, and you can pick the residual representations big enough. Right. Good. So, yeah, and other questions about the matrix? No.
So in this conjecture, about the period non-vanishing, what should I think of as this local condition? Like, is it, like specific for something in the L packet or?
I mean, so the last insights, like the representation should be globally distinguished by age, right? This, it's being locally distinct, right?
But like,
So like if it's globally distinguished.
but like if I have pi such that this L value is non-zero and the base change is symplectic, like under what extra conditions? Sort of.
Like, so,
Like, can you, for example, does there exist something nearly equivalent that has?
right, so like you can ask if you start with the base change and you know there's no zero, can you find some?
Yeah.
Right? I think it's expected that yes, but this is not no. So these boil down to some local questions, right? Which, as far as I understand, that it's not covered by this. So that implies that you can find this little pi, but maybe you have to go to some non-pure uniforms. But I think you do expect to find one, as I said.
Thanks.
Yes, it's even their work will not kind of give the result as the way maybe I would want it, right? The alpha doesn't vanish implies the sum of your vanishes, because yeah, there's this question of finding pi, which should be possible, but it's not known. That's a good question. Yeah. Any other questions? Okay, so let me try to tell a little bit about how proving this kind of things go. So, as I said before, let me start by making my life a little bit easier. And even though my theorem doesn't apply in this case, this will make the notation easier. I'm going to assume that F plus is Q and E is also Q. And let me denote R to be some lattice in this Galois representation. And I guess I'm over Q, so let me use that one. Right, so this, the proof of this theorem uses what's called Euler systems. And more precisely, this thing's called bipartite Euler systems. And I won't tell you too much what this means because it's a little bit technical, but basically, whenever you see the word Euler systems, the kind of key input, and there are some different ways of actually achieving this input, but you need to construct certain cohomology classes with prescribed ramification. So you need to construct maybe some homology classes alpha in some quotient of this class that don't lie in the Selmer group, but almost lie in the Selmer group. So, I mean that you want it should satisfy the correct local conditions away from auxiliary prime speed, and should not satisfy the local condition at the prime peak. So once you can kind of systematically construct classes like that, there is some kind of involved arguments involving global duality and Chebotarev that translates these kind of things to upper bounds on Selmer groups. So eventually you can bring this to the Selmer group vectors. That's kind of all that I want to say about Euler systems. Let me give a quick piece of notation. So I'm going to denote the quotient by these local conditions by the singular Beaumont. And I'm going to denote this quotient map by delta. So in other words, what I wrote there, we want del P log P alpha to be non-zero. We want to be able to construct some cohomology classes like that satisfy the correct local conditions, except for P. And eventually, how these are going to be constructed is that this alpha are going to be some Abel-Jacobi images of some cycles in what I'm going to call a nearby Schmerberg. And I'll describe this now.
What's this notation? The flat cohomology?
The F, yes, the local Bloch subgroups,
Okay,
which in some cases is flat cohomology, but maybe not always. Yeah,
okay.
it's I mean, for places outside L, I guess L is like L percentage is L-atic. It's just unramified cohomology. Yeah, but for places above L is more subtle. Yeah, let's not really talk about it. Right. So how does this look like? So I said, put some words here that I need to explain. So the setup is as follows. So I'm going to choose B some inert prime in F. So it's going to be the B like in there. And I'm going to consider these so-called nearby spaces. So V upper P, which is going to be V1 upper P plus V2. And this V1 upper P away from infinity and P. This is the same thing as the V1 that I started with. Now, at P is going to be non-split. Whereas V1 is split. I'm varying this prime. So for most primes, it's V1 is split. And at the Archimedean place, I'm going to take this to be signature R minus 1, 1. Whereas V1 is totally positive that. Yeah. So given the setup, I can consider the Schmerberg attached to this unitary group. So I'm just going to write Schmer VP. And this is some dimension 2R minus 1, Schmerberg. And the cycles that I'm going to consider are, well, we're going to see later that's it's not quite, but a good first approximation. It's maybe what you expect from the setup. This is some dimension R minus 1 cycle. And throughout the whole talk, I'll be kind of sloppy about the levels that I'm taking for the Schmerberg. It's true. Not writing too much on the board. But I will say a little bit about the level at P, because this is the more important one. So here I'm taking the level K with KP being the stabilizer of a so-called almost self-dual lattice. A lattice that's integral, but has codimensional one, or colength one. It's integral dual. Right, so given the set. And I guess if you know that Z is homologically trivial, but again, let me brush that aside. Then this, you can consider it safe as a Jacobi image, so there's going to be some homology class. And the 2R minus 1 about homology. Of this ambient Schmer lattice. So this has dimension 2R minus 1, so this middle good homology. And now you would like to say that the Galois representation that we're interested in appears in homology, but this is not quite true, right? Because I changed the group G, I changed the dimension space. So this Galois representation doesn't quite show up here, but turns out that you can choose E appropriately. Such that this still has at least something congruent to the Galois representation that you want. I guess I call it R a lattice. You can project to something like this. So these are gonna be these classes out for the Euler system. Of course, it's not obvious that you can choose prime speed like this, but kind of the whole idea is that when you're considering these Abel-Jacobi images, these classes are kind of automatically going to be in this Bloch Kato Selmer groups. And we want to construct something that does not satisfy the condition at P. So I'm kind of perturbing the Schmer data at P to have some chance that this class is going to be ramified at P. So this alpha has at least some chance of being ramified at P. And of course, you need to actually make this precise. So maybe you need to find some Z. So that this non-vanishing is somehow related to this period being almost. Basically, if I do this, I claim that you win, that you can apply this obvious scenario. Right. Any questions about this rough outline? Right, and so okay, so establishing something like this is pretty hard, right? Like, how do you connect to these things? So there is, yeah.
Yeah, these congruences, is where you use something like an R equals T, or is this one?
Yeah, it's that and more. Yeah. It's some kind of like level raising, right? Like some kind of repeat level raising. Like if you do the same arguments for modular curves, you're relying on some level raising. And yeah, this is known for unitary Schmer varieties. So this is part of what I'm gonna say. So this relies on these so-called arithmetic level raising. So this is a hard result. Yu, Tian, Qiao, Zhang, and Zhu. 19. And yeah, this is where the R equals G comes from. And yeah, I won't need it besides this. So, so let me denote M. And I'll be a little bit sloppy about this, but it's some maximal ideal a Hecke algebra away from some primes, but in particular away from P associated to pi. And I need to choose this prime P pretty carefully. So P a L to the M level raising prime. So these is essentially some conditions on the Sadaka parameter of phi P. And then there is an isomorphism that lets me at least have some hope of comparing these two objects that look pretty different. So let me write it out and then comment a little bit. So this is from Selberg homology. Localized at M and mod to L to the M. So basically picking the automorphic representations that are congruent to the one that I started with. And there's an isomorphism of this with functions on this Shimura set of the Hermitian space that I started with. Also localized at M and modulo L to the M. So sorry behind this is kind of complicated, but if you assume this, then this kind of answers your question, because if you like the automorphic representation that start contributes to here, and then in particular this left-hand side is non-zero. So implicitly this is saying that you can choose an automorphic representation on this nearby data that is congruent. Right. And yeah, in this left-hand side is where these classes that I sketched live in.
Is this a statement that really involves pi, or just basically a statement about the geometry of the special fiber?
Right, it's a statement for the geometry.
Okay, so the M and so on are just.
Yeah, you need to be like cusp though, and that's fine. Many technical conditions. Yeah, you're right. Right, and this right-hand side is like, you can think of this period, right? So you can think of this period basically as given by the sub-Shimura variety, given by the subgroup H. So you can think of this as maybe it's better treated as a distribution instead of a function. Yeah, so given this, there's maybe some hope of the result, right? So if if you can find some Z that maybe matches to this period here, then we win, right? If you know that the period is non-zero, this means that this is non-zero, and then you can run this Euler system.
There are previous results on the rationality of these periods? It's like this, like, so that you can make sense of it.
On the rationality.
Yeah, like, so you make sense of it as an element, the element.
So here I'm just thinking, and again, I'm being a little bit sloppy about the levels, right? But you have this maybe sub-Shimura right? H, okay, maybe depending how you choose the levels, you don't have to map. And I think of this the push forward of the constant function here.
But sorry, how does that relate to the period itself?
So if this element in here is non-zero, then there is some F.
No, but all I'm asking is, how are you interpreting this as an element in like with coefficients in ZL instead of just C coefficients?
Well, so I'm taking this map, right? It has finite fibers. And I'm just taking the function in the Shimura variety. That's the push forward, the constant function.
Oh, that's what you're saying.
Yeah.
I think I see.
Yeah, and I mean, right, like, I mean, at the end of the day, we're gonna vary this M to be large, right? So if I know that this is non-zero, then, like, if I know the period in the previous sense is non-zero, I know that this is non-zero for some large enough, and that's
Right, yeah.
right. And yeah, as actually I was alluding to this. Okay, so this map is, I don't know if concrete is the right word, but I can kind of explicitly tell you how these asymmetrical images map to, and this has to do with the geometry of the Schmurr values. So this is explained by this previous work of Lieb plus some results about the geometry in this Weibuter paper. Basically, how it looks like is that, so okay, so there's some suitable integral models of these Schmurr values that you have to work with. And you look at the special fiber. Inside that, you look at the basic locus or super singular locus. And this is something pretty concrete. So this you can prove that has some projective spaces as reducible components, as well as some Lewin-Lucid varieties of dimension R, which are indexed by certain Schmurr sets. Although there's really, you have to change the level of P. So this means some different level of P. But still hyperspecial level. And what this arithmetic level raising map looks like is that this is given by basically taking some intersection numbers of the cycle with these components. So I guess I should say if you have some cycle Z which extends to some integral model. So if you start with your cycle Z in the generic fiber, and you extend it to some cycle in the integral model. Then I can tell you what this gets me. Or at least I can tell you what's the shape of it. So up to some heck operators. Basically what you do is that you look at intersections or intersection numbers between the Z tilde and these irreducible components. So this is codimension R, this is dimension R, this is some intersection number, and similarly, you can look at some intersections. And these projective spaces. So of course here these dimensions don't match, but really intersect. So appropriate hyperplane section here to get a number. And then you combine these with some heck operators. This gives you some function on this Schmurr section. Right? Because these components are indexed by these Schmurr sets. So in some sense, this is concrete. Yeah, so really what carries this whole argument, right? And it's the first part of the title of the talk. It's this first reciprocity law. Is that I prove that there is a cycle Z such that this matches with this period. And maybe it doesn't match actually on the nose, but up to some suitable heck operators. Any questions so far? So this is basically the question, right? I have this very complicated map that these 5 objects provide. And maybe you can take the cycle that I wrote down before and compute this and see if you get this period. If you get the period, you kind of win. You can run this quite a system. Yeah, so as I just said, right, there's some natural choice of cycle, right? Maybe let me call this cycle the naive cycle. Okay. And I'm calling it naive because in fact it does not work. Well, it does work for r equals 1, but besides that, it doesn't work. Yeah. So actually, I should say that this was kind of like really surprising when I started working on this. Basically, the question that I was given is like, okay, this exists, compute what this looks like, see that it's the period, and you win. But this turned out to not work. And I want to try to explain a little bit why this doesn't work and how you can still make the arguments work. Right. So basically, if you compute what this looks like, so okay, so this kind of naive cycle looks like the period in a sense, right? It's kind of like the arithmetic analog of the period. And everything that's kind of funny is happening at P, right? So if you compute this, this will kind of match with the period away from P. So maybe I should say that this is like data series of the identity distribution away from P. But then the part at P is maybe some different function. So where this function is some element. Maybe some element in here, and it's also AG range. Right. So this think of is basically some module of spherical functions for the spherical project. Not quite, so this kind of half of that, I would note that. Right, and kind of the whole issue, or at least what I blame for this not working, like what I tell myself to be able to go to sleep for this not working, is that if you look at this module, right? So this has an action of this spherical algebra, and it is a free module of rank 2 to the r minus 1. Yeah. So as long as r is greater than 1, this is not a rank 1 thing. So you have this function that you can compute inside here, and you also have the thing that relates to the period. And what I tell myself is that, okay, this is not a rank 1 thing. I have maybe like a random element inside here. Of course, it's not random, right? But well, let me just pretend it is. Then, of course, it's not going to match this. So yeah, so to be more precise, if r is greater than 1, you can prove that the vacuum line spanned by these are not the same. So yes, this is kind of what I blame for this not working, as maybe you would expect. Because there's many other cases that people have done this kind of bipartite Auguste Selmer, and in almost all of them, you just take the naive cycle. You can compute and you see that things work. In here, it doesn't work, and I'm blaming this for this lack of local multiplicity one.
Sorry, the assertion is not that it typically doesn't work, it's that it never works.
If you take the naive cycle and you compute it, it never works as long as R is greater than 1.
Okay.
They span different hectolines. Yeah. Right, and yeah, like the philosophical arguments that I give is that I think of this as some random element. Yeah. Right, so how do you make this work? It is not.
You don't strictly need it to be the same, you just need it to be something on which you can compute the period.
That's right. Okay.
But it doesn't seem possible to
Well,
compute it other than by reducing.
I couldn't do it,
Okay.
and I have a different way of doing it. So yeah. But that's right. Right. So what I do is okay. So you can maybe philosophically, it's kind of what's the idea philosophically? Okay, this naive cycle doesn't work, so you kind of perturb it a little bit. But maybe you can imagine that you hit it with some hack operators and try to do the same argument. But okay, so philosophically, this is all well and good. You can imagine that you can compute these intersection numbers, but this is really hard, right? Kind of the main issue is that it's really hard to understand these integral models. So there's some kind of technical input that I need, which I think is kind of nice. Let me say a little bit about it. So this is building on this work of Liu. What I say an absolute contribution of mine is that basically let me give this formula named star. So basically, star also holds by replacing this integral model to some derived integral model. Maybe it's hard to say exactly what these integral models look like, but as long as you can cook up some derived integral model, you can still do the same computation, just replacing all the intersection numbers with derived intersection numbers. So this gives some more flexibility for trying to do the computation. So for example, if you imagine that you put yourself in a situation that this is, and this is a little bit simplified, but let's just say, imagine you're putting yourself in a situation that this cycle is a transverse intersection of Cartesian values, right? Then you can take this derived integral model to be, you look at integral models of these values, and you take derived intersections. So for some hack operators chosen appropriately, you can make sense of this and still have something concrete to work with to compute these intersection numbers. Right. So yeah, so I'm not gonna write down the details because it's pretty technical, but I can consider some family of like hacker translates of this naive cycle where I can make sense of this and compute all these intersection numbers. And these rely on works of previous people. These reduce to some computational referencing spaces, and these use some intersection numbers computed by Xiaoli and Wei Zhang. as well as some geometric results of Charlie Michael reports and Jacquet. Like compute those intersection numbers in terms of the ones that they compute. So there's some hard work that you have to do also to compute these intersection numbers. So exceptional that basically is what this looks like. Is that what I'm telling you is that I can consider some kind of supply of these derived integral models. And under this level raising procedure, this is going to give me some supply of spherical functions. And I want this supply to contain something, some appropriate multiple of the period. So there's some purely local computation that these functions contain kind of enough.
What is that symbol after supply?
Phi.
No, I mean the two.
Oh. BBL and Z. This you mean?
I see.
BBL for like the rats.
Yeah.
Yeah, sorry, the same thing here. Maybe this was a little bit
Okay.
bigger than there.
Yeah.
Right, and so like what I told surprise that this reduces to this kind of local computation. And I'm claiming that I can do this local computation, but it seems that this is very interesting. There seems to be some very interesting local harmonic analysis going on right there that I can't quite fully write it down, like in a good way, but I kind of like understand enough that I can still make this computation. So let me try to say very briefly some words about this. So there is some kind of parameter space that parameterizes these derived cycles. That makes you have some diagram of this. Let me write here. Spherical functions on this spherical right? And this computation of intersection numbers is giving some map like this. So this is some bunch of intersection numbers. This has a Hecke action. And I'm interested in like the image of this as the Hecke module that is spanned by the image of this, right? And these are, okay, so these are pretty explicit, but they're kind of like very messy, all these terms with intersection numbers. And what I noticed is that, in fact, you can enlarge this parameter space in a way that you can give this a Hecke action that makes this Hecke equivalent. So computing the Hecke module spanned by these, you can first compute what's the Hecke module spanned by these, and then analyze this. So this is how I do this computation. But I'm doing this kind of like very explicitly, but there should be something like to do with relative language going on behind this. And I'm still trying to understand exactly how this looks like, but basically this space should also be something like spherical functions on maybe some other spherical variety, where these two things are sense kind of deformations of each other. So X and this question mark have a common boundary degeneration. Which is GLR, 1UR. So yeah, if people are curious, I can kind of try to just explain a little bit why I think this is what's happening. from the computations that I did. And also, so this side has a hack action by this nearby space. So this open complex is also special. It's not hyperspecial. So this is just some commutative hack algebra. And there's some natural map from these coming from this theory of almost unramified representations of unitary groups developed by Yifeng Liu. And my hunch is that in some sense, this whole thing is kind of hack equivalent, but I'm still trying to make sense kind of exactly how. But from the computation that I did in here, this kind of looks like it's the kind of philosophical picture behind this, which, so yeah, so basically there should be some kind of intermediate object that is explaining kind of like this intersection numbers from the geometry, which I think it's kind of interesting, but unfortunately I still don't have exactly how this looks like. But yeah, I'll stop here. Thank you.
Questions?
The Hecke operators that you have over here, are these like,
Do you mean these?
yes?
Yeah.
Are these things that are like, that when you plug in any level raising prime, there'll be units?
They're going to be invertible. Yeah, exactly. I can tell you what this is. So there's this, I don't know how familiar you are with the 5-author paper, but this is the same notation of the 5-author paper. Is the composition of the two intertwining, right? So I said that there's two different hyperspecials. So this is the composition of the two intertwine. And this is such that its Satake parameter is the derivative of the Hecke polynomial. So the level raising condition is that exactly one of the Satake parameters is congruent to Q modulo L to the M. And this, the Satake of this is like sum of products. All right, I guess we should use it. So the level raising condition includes that exactly one of these pairs is P modulo L to the M. So this is this convention. And this is the derivative of the Hecke polynomial. Right, you also use this kind of exactly one Satake parameter of this form in the Euler system, right? This is ensuring that this local homologies have rank 1.
Awesome.
I guess when R is 1, all of the derived stuff sort of degenerates, or is this like some? Or not? Like,
Yeah, so when R is 1, these are divisors, right?
Yeah.
So they have codimension R. So you don't need to do anything fancy. Yeah. I mean, R equals 1 is basically the Heathner point case.
Yeah.
Yeah. And there's some power of P here. Yeah.
Any more questions? Not let's think Murilo one more time.